Okay, so in this first worked example, we're going to analyze this fairly straightforward beam. So we have what's referred to as a simply supported beam. So we have a pin support on the left at point A and a roller support on the right at point B. And we want to determine the reactions. So we've got some point loads on the structure. We have 2 vertical and 1 inclined at an angle of 45 degrees. So the first thing to note is we have 3 unknown reactions, which is okay because we know we have 3 equations of equilibrium, so we're going to be able to solve this structure. So this is a very straightforward process of just cycling down through the equations, constructing the 3 equilibrium equations, and working our way through it to solve for the unknown reactions. So we've got VA and HA and VB. So I'm going to start off by evaluating force equilibrium in the horizontal direction. Okay, so if I know that the sum of all forces acting in what I will call the X direction, which is going to be the horizontal direction, that has to equal 0. Now, it's up to me to choose what I want to be positive and what direction I want to be negative. So I typically tend to choose forces to the right as positive. Okay, so that's essentially the setup. So now what we can do is look at our structure and say, by evaluating the forces acting on the structure, I can say, well, I know I've got 10 kilonewtons at an angle of 45 degrees, and the horizontal component of that is going to be 10. It'll be a negative because it'll be acting to the left, so negative 10 times the sine of 45 degrees plus HA must equal 0. Okay, so 10 times the sine of 45 degrees is 7.07, and if I bring that negative over to the far side, I have HA equal to 7.07 kilonewtons. Okay, straight away we've worked out what HA is. And one other thing to note here, because the number evaluated to a positive in my equation, that means that the direction that I assumed for HA initially was correct. So I drew HA as acting to the right. Okay, and because the equation evaluated to HA being a positive number, that means that a direction is correct. The assumed direction is correct. So, and it makes sense to us. I mean, if we look, you've got the horizontal component of the 10 kilonewton force acting to the left. It's got to be balanced by HA acting to the right. Okay, so fairly straightforward. Now, the next equation, so that's the first one done. The next equation is going to be the vertical force equation. That's what I'm going to look at. So I'm going to say the sum of the forces in the y direction must equal 0. I'm going to assume upwards is positive. And let's evaluate the forces. So we've got a negative 5. We have a negative 7. We have the vertical component of the 10 kilonewton force, which will work out to be 7.07, because it's the cosine of 45 degrees is the same as sine of 45 degrees. So minus 7.07 plus VA plus VB equals 0. Okay, so let's just tidy that up a little bit, and we will have VA plus VB equal to 19.07 kilonewtons. Okay, so the second equilibrium equation has resulted in 2 unknowns. All right, but fortunately for us, we have a third equation which we can evaluate. And so the third equation is going to be the moment equation. Now, if I take, let's look at this structure again. If I take moments at any point in this structure, about any point in this structure, I am going to get the sum of the moments equal to 0. Okay, otherwise the structure will be sort of spinning off into space, and we know that it is static and it's in equilibrium. So I'm going to take the sum of the moments about point A, and I'm going to do that because 2 of the forces act through point A and so won't feature in the moment equation. And crucially, VA, which is one of my unknowns at this point, acts through point A, and so it's not going to feature in my moment equation because it does not have a lever arm with respect to point A. So when I take my moments about point A, I'm going to have an equation where VB is the only unknown, and that will allow me to solve for VB. So let's do that. Let's move over to the right hand side here so we can see the structure. So the sum of the moments about point A, subscript A, must equal 0, and I'm going to assume that clockwise moments are positive. And okay, so let's start off. So we've got the 5 kilonewtons times a lever arm of 2.5 meters, and that generates a clockwise positive moment about point A, plus the vertical component of the 10, which is 7.07 times its lever arm of 567.5, plus the 7 kilonewtons times its lever arm of 12.5, minus VB times its lever arm of 14.5. All of that must equal 0. Okay, and now you'll see that the only unknown in that equation is VB, and so we can solve for VB equal to 10.5.55 kilonewtons. And again, that's a positive number, so that means that VB acts in the direction that we assumed, so upwards. So it's positive upwards. Okay, and then if we sub VB back into our second equilibrium equation over here, we can get VA equal to, what's it equal to? 8.52. Okay, 8.52 kilonewtons. And again, positive number means that it's in the direction assumed. And that makes sense to us because we look at that structure, we look at the forces acting on it, and we know both of those reactions intuitively have to be acting up. And we know intuitively again that inclined 10 kilonewton force is going to want to drive that structure over to the left, and that has to be resisted by the horizontal reaction HA. So those are our 3 equilibrium equations employed to work at our 3 unknown reactions, and all of our structural analysis questions are going to start out the same way. If it's bending moments and shear forces we want in a statically determinate structure, the first thing we're going to want to do is calculate our reactions. Once we have our reactions, we can go ahead and calculate our bending moments and shear forces, which we're going to go on to do shortly. So continue on with the next 2 worked examples just to test yourself to make sure you're happy with calculating reactions, and I'll work through the solutions with you also.